Good morning, everyone, and welcome to the fourth round of the webinar series Resilience in Action, where we usually touch base with relevant research that helps and support the development of drought resilience in farming. I'm going to be your host today. My name is Franco, proudly representing Facey Group as the node lead of the Drought Hub project of the Eastern Wheat Belt region, a project that is supported by the Future Drought Fund, who's always focused on promoting new opportunities around this state. Today, we're really excited to have Dr. Sarah Rich and Huyen Phan, who will talk each of them about the proper research. Sarah about coleoptile development in wheat, and Huyen about rhizosheath traits and how can potentially support farming in drought conditions. Thank you both to be here today. I know that we are getting to the busy season, so I really appreciate and also all the presents. Personally, I'm very excited about how these traits can be transforming practical decisions. And on that note, I would like to hear from you. What are your thoughts? What you like to gain today? And I would really appreciate if you can unmute and share a few words with us. And no pressure if you cannot talk at the moment. Would you like to give it a start, Brenton?
Yeah, okay. Yeah, I am very interested in the long coleoptile seeding. I've tried it somewhat myself, so I'd like to learn some other things that people have learned along the way. The most success I've had is with barley. Yeah, it'd be good to hear about wheat, and yeah, also the other topic, the rhizo, I think it is. Fungicides on funguses on plants. That, yeah, I'm pretty interested in that also, Franco.
Thank you very much, Brenton. That's really great. Maybe we can have some words from Jeannie if you are here and you would like to mute. Yes, no? Oh, that's okay. If it's the case, we can go with maybe Tina, you can give us some words.
Hi, Franco. I'm the CEO at Facey Group and very interested in Sarah Rich's long coleoptile work because Facey Group hosted a site and supported her in 2023 now, and love to hear how that work is progressing. And great to meet you again, Huyen. Yeah, thanks for organising this.
Thanks, Tina. It's great that you have touched base with both at the same time, so we can have a good discussion about it. If you maybe read, you can tell us a little bit about what are your thoughts of, or what do you like to learn about this particular webinar, if you're able.
Hi, I'm just I just work in the industry, and I was just tagging along to see if I could get some learns and some takeaways. Yeah, just observing in the background. Thanks.
Yeah, right, that's all right. Thank you very much for sharing. I do appreciate everyone just giving a couple of words and make this more dynamic. So thanks for sharing. I would like to ask you all that any kind of question that you have, I would like to formulate, you either pop it in the chat, we will have it later for the Q&A, or just hold it with you at the end, so we can just properly make this more dynamic or keep that dynamic going on. All right, to kickstart this session, I will like to have ask Dr. Sarah Rich just to put her presentation on. Dr. Sarah Rich is from CSIRO. Who will present her work on coleoptile length and emergence. That's a key trait that allows wheat seedlings to establish from deeper sowing depths. And she will touch base with a project that is a multi-site trial project across Western Australia as she worked for several years. The stage is yours, Sarah. Thanks.
Okay, thanks heaps, Franco. So, as Franco mentioned, talking about long coleoptile wheats, and the work I'm presenting here today is mostly coming from a large GRDC-funded project onto long coleoptile wheats that's been led by Dr. Greg Rubetsky, who's based over East. And most of the field work, which has been presented here, is actually being run by SLR Ag out of York here in Western Australia. So I just wanted to start by just setting the ground for deep sowing and what scenarios are actually going to benefit from deep sowing. And what I'll focus on today, being a future drought fund, a drought hub talk, is around moisture seeking. And this is probably the aspect of deep sowing that's received the most attention. And that's because, as we're all aware, particularly here in Western Australia, with those changing rainfall patterns. So that is for some people actual changing annual rainfall, but for a lot of growers, it's not that annual rainfall that's changing, it's the timing of those rainfall events. So for most people, we're finding it's those autumn rainfall where it's becoming more patchy or becoming lower. You can see from the graphs I've put up, which are from DPIRD of the median season break from the mid-70s up to the turn of the century, and that's in that kind of May, even in April, down in those really high rainfall zones. Whereas you look at the break of season I just realised that we might be on there. Is that better? The break of season in the last 20 years, and there's a lot more of that brown, which is the late May into June kind of breaks. And obviously the timing of the break's important, but we're also finding that there's often these scenarios where the break comes, but then you're getting a month, 6 weeks, even up to 8 weeks of no rainfall after that break has come. And so what this ties into is impacting early sowing. Obviously, a lot of growers dry sow now, it's kind of the status quo, but that's also that risk taking of picking your variety on when you think the rains are going to come, and that's becoming harder to predict. And deep sowing can also be fantastic on those non-wetting sands. If you've got that moisture at depth and you're only getting really small rainfall events that just aren't actually breaking through on the non-wetting sands. It also can be a great advantage if furrow infill is an issue. The photo I've got up there is from the really big blow, I think maybe 2020, that came through, where a whole bunch of those surface soils, particularly if you're on sands, have just come and filled in your furrow. And so suddenly you've got an extra 40 or 50 millimetres over your seed. And also fantastic on ameliorated soils. So if you're working on something that's soft, or you're sowing across rip lines or anything where your depth control is not so great, having something that can get up from depth is really beneficial. And there's work being done now, which I'll touch on later in the talk, around whether deep sowing can also be beneficial around avoiding the phytotoxicity of preems. We all know that preems are getting more and more kind of effective and nasty, I guess, and so plant backs can be quite a lot deeper. I think Overwatch is already recommending a 30 or 40 mil plant back, and also around disease avoidance and whether deep sowing can be beneficial there. So setting the scene, I think one of the most misunderstood parts about long coleoptile wheats is actually what the coleoptile is. And part of that is because it's a really transient organ on the plant. So essentially when the plant germinates, the coleoptile protects that first leaf as it's emerging up out of the soil. So all it is an organ that, as soon as it senses the light and breaks through the soil, splits open and the first leaf comes out. Or if it can't sense the soil, it grows as long as it can, and it still will just split open, and that first leaf will emerge and do its best to get out. So you can see in the picture there's a close-up showing that coleoptile that's split open and the first leaf emerging. Modern elite wheats, so most of the wheats that we plant, tend to have 40 to 70 millimetre long coleoptiles. And I've just got a picture here of an older wheat, so it's kind of got one tiller going. And you can see there that there's the remains of the coleoptile there. So that's already starting to break down. And so if you dig up wheat that's much more advanced from this, and even if you dig up wheat at this point, often the coleoptile is totally degraded depending on the season. You can't actually see it. And so what a lot of people think is the coleoptile at this point is actually the subcrown internode, which is just something that's grown up from the seed and pushed the base of the plant up inside the coleoptile. And yeah, often the coleoptile is not even there, which can create some confusion. It's really just in that early seedling to help the seed get out of the soil. So what impacts coleoptile length? So it's genetics, and that's the big thing, that the main thing. And so basically really old wheats, the Green Revolution, they were all really tall, floppy. There was lots of issues with lodging. And the Green Revolution introduced these dwarfing genes, so reduced height genes, which were great. We've got the short-statured wheat that we've got now. We've had huge yield gains that have come along with that. But most of the reduced height genes that are in our elite wheats. So RHT1, this is RHT is the reduced height gene name. RHT1 and RHT2 are what are in most of the wheats that we regularly plant. And as you can see from this bar graph I've put up, they're reducing the coleoptile length by 4 or 5 centimetres. And obviously, if you're sowing your wheat at 3 centimetres, who cares, right? They still gets up fine, not a big deal. But now we're trying to search for moisture. We're trying to get deeper sowing. We also obviously don't want to lose all those benefits we've had from all that breeding and the short statured wheats. But luckily, there's a whole bunch of alternate genes that we've got. And that's what breeders are starting to work with now to get into wheat. So crossing them back into those elite backgrounds that we've got, but still then using an alternate gene that still gives you that short statured plant, reduced biomass and great yield, but doesn't affect the coleoptile length. It's only reducing the coleoptile by maybe 1 centimetre. So if you go to trials, often you'll see that there's something like MACE and MACE 18. All that's actually indicating is the fact that it has the RHT18, so this reduced height 18 gene. And that what that does is it gives you the longer coleoptile. As you can see in this picture, you've kind of got coleoptile lengths of 6 or 7 centimetres in the standard MACE, but with that alternate dwarfing gene, you're getting coleoptile lengths of more like 12 centimetres. The second thing that impacts coleoptile length, it's really important for the way that we grow wheat, is temperature. So you can see there are a whole range of different varieties with different coleoptile lengths. Most of them are 6 centimetres up to 12 centimetres. That's at 15 degrees constant. If you measure them at a constant 20 degrees, the coleoptile lengths are way shorter. So basically, the colder it is, the longer the coleoptile. So if you're sowing in June, you know, your soil's going to be cool, maybe, and you're going to have longer coleoptiles. But obviously, most of the time that we're talking about deep sowing, it's tied in with early sowing. So we're looking at those hot late summer, early autumn days where we're chasing moisture that's come from an early rainfall event. Soils are going to be warm, potentially even warmer than 20, and so your coleoptile lengths are going to be already way reduced. And so what that means is those genetics are really, really important to try and get the longest coleoptiles possible in those warmer soils. And the third thing that impacts coleoptile is obviously your seed size, and your seed quality. I mean, and that kind of goes for everything. You know, your bigger your grains, your bigger your coleoptile, and also your thicker your coleoptile. And we have found correlations, obviously, with a big thick coleoptile with its ability to push up through the soil. And also, not surprisingly, if you're comparing plump versus kind of pinched grains, the plump grains are going to produce better coleoptiles. So that's just sort of some background there. And because I'm really focusing on moisture seeking and trying to actually deep sow to get into that moisture, I'm going to focus on a bunch of trials that were run around Western Australia. These were all run by SLR last year as part of that big project I talked about. And part of the reason I'm focusing on these is last year's season was just so perfect for deep sowing. It was just like this beautiful illustration of when deep sowing fits. And the whole thing about deep sowing that we always try and talk about is that it's a management technique that you should really only use appropriately. So if you've got moisture through your whole profile, just shallow sow. There's no benefit to it. And so last year, there was that moisture at depth. So SLR got all these trials in at these 6 locations kind of from early to mid-April. And they pretty much were all sown into soils which, you know, were like this, where you had that really dry topsoil layer. So the shallow sown, which kind of went in at 30 or 40 mils, they were just into dry soil, essentially just dry sown. But those deep sown plots all actually went into moisture, with the exception of Kalani, which we thought it had got into moisture, but I think it was right on the boundary of that moisture. It was a really dry, friable soil. And so basically the deep sown was also dry sown. And so what you can see by getting into moisture is those deep sown plots got away by sort of 2 to over 3 weeks ahead of when the shallow sown plots emerged out of the ground. And so that's a huge amount of extra growth and biomass that they're going to be able to put on due to that. Kalani, they both just came up in June when the rain eventually came, which was not the best result, but is a really good illustration that you want to be confident that you're sowing into moisture, because otherwise you're not getting the benefit of deep sowing. Deep sowing into dry soil is going to be a disaster, right? It's not what you want at all. And so just as an example, this is some emergent count data. You can see from the photo of the deep and the shallow, you can see that the shallow sown that were into the dry they're a lot less advanced. And basically what this is showing in the dark blue is a 12-day count after sowing. The brighter green, I guess, is a 24-day count, and then there's a 54-day count. And so you can see that those in the dark blue, pretty much everything, all the deep sowing had started to come up at 12 days because they were in the moisture. And you can see that those longer coleoptile lines, the Mace 18, the Magenta 13, Caliber's kind of a mid-long line, they were starting to come up. But the other thing you can probably notice is, so by 54 days, everything's up. Those dry sown ones had got some rain, the shallow plots were all up. But the deep sown ones didn't actually have the same total emergence. And so if we look at just total emergence, so what this graph is a reduction in emergence graph. So it's comparing the shallow and the deep sown. Shallow sown will usually end up with more plants per metre squared coming up. And so what you can see is those longer coleoptile lines, the Mace and the Magenta 13, they've got maybe 10 or 20% less plants per metre squared in the deep sown plots. But those shorter coleoptile lines, your Septa, your Mace, those have got quite a lot of reduction. The different colours are the different sites. And so you can see some sites like Drought and Bunteen had really significant reductions. You know, your 60 or 70% less plants were coming up in those in those deep sown plots. So deep sowing, there's a whole bunch of factors that play in. It can be your soil type, it can be your moisture, it can be your temperature. And I'm just going to get, if you have a look at the pink ones, that's Kalani, because what I'm going to show you next is the yields from here. And so the yield reduction from sowing at 110. So what you can see is, even though there were those reductions, those long coleoptile lines, the Magenta 13, the Mace 18, there really wasn't a significant yield reduction in the shallow plots. So even though less plants were coming up, last year was a pretty, we had that warm, wettish kind of mid to late finish in there. So we actually ended up with quite a lot of tillers on these. So even though there were less plants, things did fill out. And so, Septa, right? It still did really well. But then some of those other lines, which did have that really big reduction, there was still a yield reduction, but it was nowhere near as extreme as you would have expected from the amount of lower emergence in those deep plots. But, those long coleoptile lines that are made to go in deep, barely any yield reduction, which is a pretty fantastic result. Another thing that we really noticed was that our deep sown plants really stayed greener longer. They just really hung on as the season finished off. So obviously there was slightly reduced numbers there. So we were like, maybe better water use efficiency, but we were really intrigued to know if they actually were getting deeper rooting. So if those extra 2 or 3 weeks of growth was actually correlating to more roots at depth, and therefore more access to soil moisture later in the season. And so we don't have our own root corer here anymore. So we actually hired a geo-approved direct push corer. The guys that were absolutely mad, they're not usually used to doing a couple of cores for, doing soil toxicity or something. And they just spent 2 days out there doing all our coring for us. And essentially we're coring down to 2 meters and then checking where the deepest roots were in those. So we could actually correlate with the plots and the varieties, how deep in the soil and in the profile the plant roots were going. And what we found was that with earlier emergence, so those extra few, this is at Bunteen, these pictures and the graph that I've got up. So they had 19 days of extra growth by being sown in deep and getting into that moisture. And we found that 19 days gave an extra nearly 20 centimetres of root. And so therefore, potentially quite a lot of access to soil moisture. And so the impact of that little bit of extra soil moisture at the end of the season, depending on when the season ends, could be huge. Last year with the end of the season, there was in a lot of the north, up to the north and into the east, there was not great low test weight, some screening issues. And there really is that potential correlation. If you could get your crop up really early by sowing deep into moisture, that you could really have that access to moisture at the end of the season and, really help by improving your screenings. Obviously, some of this rooting work's early days and we need to get a lot more sites done, and doing the soil coring is pretty expensive, fiddly work, but we're really hoping to try and pick apart some of those relationships. Other work that's just really getting in there is the fungicide and disease work. So there's a bunch of trials out there at the moment that are being done. results are still kind of to come. We're finding that this is obviously really seasonally variant. It's really location variant. It's really variant on what's happening in those exact sites. So we're trying to do a whole bunch of trials so we can actually start to pull together an overall picture. But one of the questions I've got asked heaps is about rhizocke avoidance. And so I just wanted to present a quick couple of pictures. So we found in our trials that we were finding that our shallow dry sowing, as opposed to our deep sowing into moisture, in a site where we had rhizocke, even just doing, you know, these kind of quick shovel and have a wash off of the roots, that there did appear to be more root mass on those that were deep sown. And we found this interesting. So we picked it apart in a pot study. So this is the work of a guy called Jonathan Anderson here in Florida. And so what he was doing was actually setting up really big pots with roots, with plants, and he was sowing the deep sowing onto just uninoculated soil, and then putting 10 centimeters of soil that had been inoculated with rhizocke on top, and sowing those shallow sown ones into there, so we could see what could happen. And so this is just magenta 13 that hasn't been inoculated, and so you can see there's the deep sown and the shallow sown. They don't look that different. They've both got a healthy root system. Everything's great. And we're finding that then once you actually looked at the rhizocke, that there really seemed to be a huge impact of that deep sowing if the seed was actually put down below that rhizocke layer. And rhizocke only does tend to usually be in those surface soils. And so as you can see here, this is taken, they're not really mature plants, but they should have nodal roots by this point. So even though that deep sown one has a great seminal root system, so those primary roots that come out of the seed, you can see that those nodal or tiller roots that normally are emerging from the base of the plant, they seem to be being impacted by the rhizocke and not growing down through that soil layer. So obviously comparatively, the root system of the deep sown is far better than that was actually sown into that rhizocke layer, but we're still trying to pick apart what those long-term effects are. So roots are incredibly able to adapt and change with their environment. And so potentially that seminal root system would just fill out and would take over the whole role. Normally the nodal roots and those roots growing from the base of the plant end up being part of the main root system. So we're still unsure, but we need to take this work further into bigger pots and more mature plants. But at the moment, it's really looking like deep sowing could have a role to play around avoidance of rhizocke. So just kind of wrapping up, the key message is that Coleoptile genetics are advancing through the breeding program. So pretty much all the breeding companies are using some of those alternate dwarfing genes and back crossing them into their elite wheats. We already have Bale and Jewel that Longreach brought out 2 or 3, maybe 4 years ago now. So hopefully that's starting to filter through as being available. All the other breeding companies are starting to bring it in. But for WA, we've also been looking a lot at those kind of mid-long coleoptile wheat. So this is things like Caliber, which isn't necessarily going to produce a 14 centimetre coleoptile, but we've found that even if you don't have a super long coleoptile, as long as you've got a decent length, if you're sowing onto those sandier, light friable soils, as long as you don't have a really heavy crusting layer, a lot of these are actually getting out fine. I mean, Caliber is not a long coleoptile wheat by any stretch of the imagination, and we've had some amazing results with it on really friable soils of actually just managing to get out from quite deep depths. And so there's a lot of variety available in Western Australia with currently available options. And there is work being done to try and produce a standardised way for breeding companies to produce or present their coleoptile data. It's really confusing when you're trying to look at variety sheets and it just says mid-long coleoptile, you know, what does that even mean? So we're really trying to work to make, and the breeding companies are on board with this, to get a standardised way for the breeding companies to measure. And so that's always presented. You know, obviously if one breeding company's measured at 15 degrees and one at 20, you can't compare that data. And it's just really confusing. So hopefully that will start rolling out on variety sheets as a standardized way for this information to be presented. Aside from that, so I think it's really the data from last year and this year is just backing it up, and we have national trials on this, is that deep sown wheats will definitely get earlier germination if they're sown into moisture at depth. And those with the longer coleoptiles will only show like up to 20% reduction in establishment. And that is not necessarily going to have any impact on yield, having that reduction. I mean, yield is obviously that balance of the timing, the number that comes up, that variety in the season. But those long coleoptile weeds, if the season's right and yet they are into moisture and they're getting up early, we aren't getting a yield reduction. And we are showing that early establishment is so beneficial going through the season for getting those deeper roots, particularly if you end up with those, hard, hot finishes where that deep soil moisture is just so important. So yep, depth can help with avoidance of rhizoc. Still working out on the long-term tiller root impacts. And there's also work being done around the preems. And that's showing some interesting results, but it's a bit varied site to site. So they're not kind of rolling out those results yet anywhere. And I think, as always, I'm obviously really involved in deep sowing research, and I think it's this amazing tool, particularly going forward, that we're going to be able to use to get around some of these changing rainfall patterns. But I think it really is a tool that has to be used in the right spot. So I'd be really wary about deep sowing if subsoil moisture is really limited. So obviously you don't want to, if you've just got that band of moisture that's come through from, if you have a really heavy dump and it hasn't soaked in very far, sowing into that, if it's bone dry down to depth, is not great, because if you get your crop up, it's got nothing to use if you don't get any more rain coming through. And the same goes for if there's no benefit to deep sowing generally, if you're actually do have a full moisture profile. So it's got its fit, but it's not going to be a fit for every season or every paddock. It's about playing around and working out, but making sure that you are actually going to moisture. Our example at Kalani, where we thought we'd tipped into the moisture, but we were just ticking along the top on a really friable soil, is a good example of how it can go wrong. But hopefully, as these genetics roll out, it'll be the type of thing that we'll have long coleoptile genetics in most of our varieties. You can plant a long coleoptile wheat shallow. It's happy as, comes up shallow as soon as it senses the light, that first leaf goes through. So yeah, I think the future's looking really exciting for deep sowing. And these varieties that are starting to roll out from the breeding companies are looking really exciting in terms of their ability to emerge from depth and still yield really highly and have that disease resistance that we're kind of used to in our elite wheats. And so I think I'm probably at time. I will wrap up. Thank you very much.
Yes, thank you very much, Sarah. That was a really insightful presentation. I just keep in mind all this interaction when you deep sow wheat, and how you choose your variety. So I reckon that gives you a lot of thought on the timing and how you can take advantage of that. Now, just to keep up with the webinar, thanks, Sarah, again. I would like you to ask Huyen, if you're there, if you can just start sharing your presentation when I just make the introduction. So we will have now Huyen Phan, who is a doctoral student at the University of Western Australia at the moment. Her research is focused on the genetic diversity of rhizosheath, which help plants to connect to moisture in dry conditions mostly. So Huyen, when you're ready, please.
Hi everyone, my name is Huyen. I'm a PhD student at the University of Western Australia. Here I present one part my PhD project with the impact of rhizosheath size in the root growth with the water use efficiency and grain use in wheat in acidic soils with high aluminum content. And this is part of my project funded with the Future Drought Fund, with the Southwest WA Drought Resilient Adoption and Innovation Hub, and also with the other funding from my government, UWA and WAC. My supervisor team is CD, Jain, CSIRO, and Shasha. Okay, next slide, please. I'm gonna talk a little bit about myself. Was born and grew up in Vietnam. I got the bachelor degree in Thái Nguyên University. And then I spent 4 months in Switzerland to do like research, intern with the root analysis and supported 2 PhD project. And then I got the master degree in Japan, doing kind of the the accessing with the Beer Valley at the seedling stage in the waterlogging, and then back to Vietnam, doing the project in climate smart farming. And then 2023, I came to Australia to study at UWA. Next, please. And here is the content of my talk today. I'm going to cover the importance of crop root system, the challenges in acidic soils, the role of rhizosheath soil, and I will share with my hypothesis research and update with the method, the results, the conclusion, and the next step with my study. Next, please. Let look at the importance of root system. We might hear about the deep sowing along Coleoptile genetic from the Dr. Sarah Rich from CSIRO. So here, that's quite the below surface, and I'm going to share the importance of them. So root system quite the fundamental thing for the crop productivity for sure. And this can help to overcome some biotic constraint, quite critical to maintain the structure, the functional property for sure. And absolutely, we need to pay great attention, especially in the breeding agronomy program, and particularly in the rainfed environment. If you look at in the right side of slide, I shared the root study with the plant science, and you can see the x-axis with the represent the decades, 10-year periods, and the y-axis shows the percentage of root study per the plant study. So we can easily to see that, like even now, about just 30 to 35% of paper published in 10-year time frame are devoted to roots. The majority of research focus on shoot, with the researcher often drawing conclusion without considering root system. Next, please. So think about the challenges globally. I want to bring the attention with the acidic soils. You might all familiar with that, but let me recall everything. Acidic soil cover about half of global lands, and when the soil pH drop below 5, the aluminum becomes soluble and toxic, and it directly harm roots, even limiting the growth and function. Plants hard to get the water and nutrient, and at the end it causing the yield loss, even up to 25 to 80%. And here in Australia, you can see the color in the graph in the right side. The red and zero color represent the pH. I mean lower than 5.5. In Southwest WA, especially 72% of topsoil and 45% of subsoil pH, just lower than optimum pH for the crop, and it even losing about 1.6 million Australian dollar for the lot grains production. And next, please. There's many ways researchers find to give or bring attention to overcome such kind of condition in acidic soil drought condition. But here, I want to introduce you a specific thing as a fascinating structure in plant we call rhizosheaths. It might be not really familiar to all of you, but you might see them frequently in the field. As the rhizosheath structure comprise with the root hairs, ashes, microbe, and soils, of course. Why does it matter? Because it can crucial for helping plants get water and nutrient, especially when they are dealing with drought, acidic soil, or even with the aluminum toxicity. You can see the middle of the slide. That's in my with root system. When we're holding the root and we gently shaking the root system, the soil still remaining surrounding the root is called the rhizosheath. So even in the field, in the right side of the slide, that is a weed root. we collect from the field just few days after showing, and abundance of soil surrounding the root is absolutely the rhizosheath. Next, please. Yeah, it's a bit with the exciting research finding I want to share with you. The Emmanuel Jahal from CSIRO, he discovered that the root hair length and aluminum tolerance are crucial for rhizosheath size in wheat. So we can simply understand that with the longer root hairs mean better in rhizosheath. And so what? So what? In acidic soil, it can enlarge the rhizosheath and root hairs, and then improving the wheat yield at the end, even under phosphorus deficiency and water stress. It sounds interesting because we might think like in the deficiency condition of nutrient, the root system might be smaller, or it can be hard to get the water and nutrient. But now here, with the support of rhizosheath, something can happen. Next, please. That is the thing. We even are not entirely clear about how rhizosheath actually work. We know they're important, especially for wheat and water and nutrient uptake. But for mechanism, it's not really understood fully. We have some studies suggested that wheat with larger rhizosheath might have better biomass, better nutrient uptake, and higher juice, but it hasn't been conclusively proven. And we definitely need on genetic basis on rhizosheath to help with aluminum toxicity. So here is what I'm wondering. My research question, like do wheat variety with bigger rhizosheath actually have better root system? And next, that's why I do with hypothesis that the wheat lies with larger rhizosheath hypothesize to develop bigger roots, use more water, and more grain juice than Joe with a smaller rhizosheath. To answer the question, I try to address with two aims. Firstly, understand the root traits with different wheat lines grow in acidic and high aluminum content soil. And secondly, measure their water use, wind use, and water efficiency. And next, to set up my experiment, that's all done in the UWA glasshouse in 2024. I set up two experiments separately in the rhizobox. We can see through the root surrounding the box, and the second experiment is the PVC column. So with the rhizobox experiment, I do the weekly root tracing to observe the root grow weekly, and I can get the root data every week, and then I can get the root architecture, the rhizosheath soil biology data. With the PVC volume, I weekly do the water and recording to see the water use efficiency and the harvest index at the end. Next, please. So the rhizosheath size or rhizosheath biomass, someone might curious to know how we can collect them. It's a bit tricky as many researchers try to mention the method that we can collect it because it's quite sensitive to get it. That's why based on Pang 2027, I follow that kind of method to collect them by generally extract the roots from the soil column, and then we gently agitate the root to remove loose soils, so the soil naturally stay attached. That's in rhizosheath, like I told you. To measure it, we submerge the root in the calcium chloride solution to release the soil, filter it out, dry it in oven for 2 days, and then weigh it. And this gave it our rhizosheath biomass measurement. Next, please. For my experiment, I used 4 wheat lines with different rhizosheath size. S1 and S2, that is the breeding lines with smaller rhizosheath, while L1 and L2, that's a large rhizosheath size. And I also use the maize, the commercialized parents that also have the small rhizosheath size. Just for the soil in the right side, you can see we went straight to the melting in the WA wheat barrel, and we collect the soil in 4 different depths to match the real field condition from topsoil to 0 to 10, 10, 20, 20 to 30, 30 to 100 centimeter depth. So what interesting here, the soil property changes with the depth. In the topsoil, the pH 4.6 and go deeper. It's at 3.9, and it converts with the aluminum content in the topsoil 6.6 and go deeper. It's even up to 27. So we test the plant in exactly soil profile without any lambing, like the farmer do. So to see what happened, like the wheat with the different rhizosheath size can activate in such kind of serious condition. Next, please. Oh, this is quite busy graph, but I'm trying to help you to digest it. You can see here, we harvest the plants in the rhizobox and measure at the 77 days after showing, and we got some result here. You can generally see that in the x-axis, it means the width line S1, L2, L1, L3, and maize. And in the y-axis is the rhizosheath trigrade, total root length, root biomass, and root length density is calculated by the root length per soil volume. So overall, width lines with large rhizosheath, L1 and L3, shows the clear advantage over the small rhizosheath side, S1, L2, and maize. And even you can see like L3 develop the longest root system, while S1 has a shortest one. It's quite interesting here. We use the indicator of root length density. So root length density is mean the root length per soil volume. It's higher in L3. It indicates that the better exploration for the water and nutrient happening in L3. It means like in the same condition, L3 might have more advantage compared to the others. Next, please. We also tracking the root development over time. You can see the cumulative visible root length in the left side of the slide. In the x-axis, that's the days after showing, 7 days onward, from 7 to 77 days after showing, and the y-axis is mean cumulative root length measured by meter per plant. You can see that L3 consistently outperformance of all other lights, with the difference appearing as the 14 days after showing, and showing the big difference from 42 to 63 days after showing. So this is before and after voting stage. And by 77 days, we can see like L1 and L3 is mean the larger rhizosheath side width reach even 1 meter depth. In the right side, you see the root system that I tracing at the end and captured by camera, and to compare by the width line in the condition. And L1, L3 reach even 1 meter depth. How amazing! While S1 and L2 just only reach about 0.7 meter and maize just 0.85 meter, with the different pH and aluminum content here. And I can answer the reason why after that, but you can see it no much more difference among 0 to 0.2 meter depth, but it profile and longer after 20 centimeter depth in L1 and L3. See how the advantage in the deeper condition. Next, please. That is also root distribution along the soil profile. You can see that is the rhizobox I use in my experiment, 1.5 meter with the with the root system here, I tracing weekly, and this is nearly the end, not at the end, but nearly at the end. I capture them, and the right side, that is the tree graph with the root length, root biomass, and root length density. The y-axis means the soil depth from 0 to 1 meter, and we can see somehow they show the differences in the soil profile. In the previous slide, I just mentioned that. Okay, so for the one panel, we can see no much difference from 0 to 20 centimeter. But here, when we collect them by open the glass of the rhizobox and chop down in each soil profile, get this wash the root and then scan them, got the data, root length and root biomass, and we can see how the real differences. From 0 to 20 centimeter, L1, L3, and maize even show greater root length and root biomass in the top 20 centimeter compared to the smaller rhizosheath side wheat, S1 and S2. And the root system of the lines L1 and L3 even more profiles below 20 centimeter of the soil profile. That's linked with the previous picture I showed you before. And even when pH below 4.2, just around 3.94, and aluminum content except 21, is still alive and go deeper. Next, please. After harvest, the last rise, you can see in the picture, we capture at the anthesis stage in 5 different wheat lines at once, at 2 maize and L1 and L3 in the picture. They show some shoot biomass differences, and it even I show in the table here the grain juice is biomass of 5 different lines. The L1 and L3 in large rhizosheath line yielded approximately 17% compared to S1 and S2 smaller rhizosheath side. It aligned with the previous data consistently to show the outperformance compared to the other. And in the right side, that's the data from the pre and post antacid water use and the total water use. And obviously, L1 and L3 use more water throughout entire growing season. It's likely due to the larger rhizosheath enabling deeper or more extensive root system below 25 centimeter depth, makes them needing more water compared to the other. Next, please. Next, please. Okay, it's quite busy graph. Even can you come back? Okay, here this is the patient correlation. We try to see the correlation between the rhizosheath side compared to the other planches measured at the first harvest, 77 days after showing, or even with the other data at 135 days after showing. It's quite busy graph, but the interesting here I want to show, this is the rhizosheath side with the green juice. It's quite important because it's positive and correlated. The result is 0.78. It means that like the rhizosheath side strongly correlated with the green juice. It means like the large rhizosheath line showing the superior performance due to the better characteristic, and it's because they get more nutrient and water capture capacity. It's quite the interesting indicator for us to select the light for the better green juice in the future. And next, the result I have so far here is the wheat line selected for the rhizosheath side retained large and small shade when even they grow in acidic soil. Large rhizosheath side even coupled with the deeper, more profile root down to 0.2 meter, even the pH drop below 4.2 or aluminum content except to 21 milligram per kg. And interesting, like rhizosheath side slightly enable more water use and boosting shoot biomass and green juice at the end when we compare to I mean experimental setup is still consistent with the data and the performance of them. Next, please. I have the take-home message here. It's quite straightforward. In my research, it's simple. Like large rhizosheath size is stable, hairy turbocharge in weight, that support deeper root growth and higher juice, making it a promising target for breeding in acidic or rich aluminium soils. Next, please. Okay, so to finish this kind of experiment last year, we continue doing with the soil biology data to see how the bacteria community in the rhizosphere work in the different weed lines. We expect that in the large rhizosphere weed line, the bacteria there might be more than the community there might be more than in the small lines or some kind of interesting light in bacteria enable in such kind of condition. And I'm gonna share with you really soon. In 2025, to confirm with the data I have last year, I keep doing with two big experiment in first use efficiency, low condition, and also with early season drought. And we expected that like because here, the drought season always happens at early stage, and they hardly to get the more water. The excited result coming, and I'm nearing at the end of my experiment and hope to share with you really soon. And next, I think that is the next one. The last slide, I want to acknowledge the funding I got from Vietnamese Ministry of Education and Training, the WAC, WA, and also the Future Drought Fund with the Southwest WA Drought and Innovation Hub. And thank you for listening.
And thank you, Huyen, for that insightful presentation. I'm pretty sure that that research will lead to some other research, other results that we can discuss. So I would like is for us to proceed to what it will be the Q&A. Since I have seen one question from Brenton that is directly addressed to Sarah. That it says, on dry sowing, any observation in the field with farmers on pre-emergence or ways to edge beds with seed depth, increased rain comes or patches of soil don't germinate? That's a direct question that is on the chat.
Yep. I can. Yeah, can you hear me?
Yes.
So I can share a few comments about preems. I'll actually just share a slide because that will just be slightly easier. So these are some, we have done a bunch of work on some on preems and on other herbicides. It's really early days, so part of it I didn't present it as it's not conclusive. So this is just take this with a grain of salt. This is some preem work. So basically we found looking at these herbicides, and these were tested at 2 times label rates, obviously, which is not recommended, but we were really wanting to get the example of what was happening with these. And so we found that this was deep versus shallow. So the shallow were dry and deep were into moisture. And the deep sowing showed no reduction in crop emergence from control using any of the herbicides. The shallow sowing showed reduced emergence in the 3 that I've got listed there. And the trifluralin was by far the most extreme. I didn't look at this data because I wasn't going to talk about it today, so I can't remember the exact numbers, but I can remember that it was by far the most. And we also, these were all scored for phytotoxicity in the seedlings as well. And so oops, what am I doing? Yeah, so deep sown once again showed really minor phototoxicity, so pretty much none. I mean, deep sown plants sometimes have a tiny bit of yellowing when they've come up anyway, just a little bit of stress, but disappears. So they showed no difference really to the non-treated controls. The shallow did show higher phototoxicity than the controls, so the ones that hadn't had any herbicides on them yet. Overwatch was by far the most, and then we had a bit of variation. Metribuzin was the least, and most of the others kind of were in that 6 to 8%. So they all were quite low in terms of phototoxicity, and all of this did just disappear over time. It's not like it was an ongoing impact to them, but obviously those early seedling stages, I'm biased because it's a part of the system that I work on, but they do have that huge flow on impact. So that's some really early indications, and we have had anecdotal evidence or anecdotal stories in the field, just talking to farmers and like people that host our trials. So people are, particularly in some of those wetter environments where they're looking at deep sowing less for moisture chasing, but more for trying to play around with some of these other things like disease and herbicides, that they have had some success with being able to be pretty heavy-handed on their preems and avoid any impact by sowing that little bit deeper. So that's the question on preems. Hedging your bets with seed depth, that's such a hard one. Yeah, it's always a gamble, right? Every time you sow, it's a gamble. So, I mean, realistically, if you've sowed you deep into moisture, if rain does come on those, it comes, you're going to know if rain's going to come in 3 or 4 days. Hopefully the Met Bureau is that good. So it's unlikely that, if it comes and it's that week or 2 out, those deep sown ones will probably end up emerging at a similar time to anything that you'd sowed in shallow. So it's about taking the gamble, doing your best you can with all the weather models we've got out there. Yeah, patches of soil, that's hard. I mean, it's a really tricky one there with your soil types. And our hope is as these new varieties come out with the longer coleoptile genetics, they're going to be even stronger and better at emerging well. I think it's just about going in deep if you've got that moisture at depth and it is dry and it doesn't look like there's any rain coming. And, if it looks like there's a big dump coming in the next 6 or 7 days, I probably wouldn't recommend it. But yeah, it's doing what you think is going to work. And obviously you're on a non-wetting soil, there can be still huge benefit even if you do get those rainfall events, because obviously unless it's really heavy, you're often just not getting that infiltration anyway on the moisture. Yeah.
Thank you. I would like to ask Tina. Yes, you have a question?
Yeah, sorry, Sarah. We're talking about that deep stored soil moisture. Are there any particular sort of cutoffs you'd look at for us? You were looking, one of your charts showed summer rainfall and things like that. Is there any particular no-go situations you would think about with early rainfall and summer rainfall to be able to feel confident that you've got the moisture you need there?
There isn't, and it's something we talk about a lot because soil moisture is so tricky, because obviously you can just, everyone just digs around and feels and sees, and if you can feel that there's moisture there, there's usually moisture there. But unfortunately, even if you want to go hardcore and actually take a sample and dry it in the oven and work out how much moisture is there, you've got volumetric, which is kind of, depending on soil type, it's really variable how that actually impacts how the plant grows. I mean, we keep talking about the dream would be to have something like a COVID stick test or something you could just stick in there and it kind of says there's moisture or there's not moisture. We don't have anything yet. It's really hard to give hard and fast rules because soil moisture is so soil type dependent. Yeah, so I think it's if there's moisture there, and I think if there's moisture sitting in the band that you're sowing into, and you can dig down a bit, and there's a bit more going deeper, like if you take a couple of shovelfuls and there's actually moisture down deep. But if it is one of those, you sometimes get those thinner bands that's there, and it is still bone dry deeper down, I'd be a little more cautious. But once again, it depends on the season that you've got coming through, so it's hard to give really hard and fast rules, unfortunately. Yeah.
You can't sort of base it on the summer you had?
Oh, you can. I mean, I think if you know that there was some moisture that came through over the summer, I mean, I think depending on what you had in last year, once again, that depends, if on some of those West Australian soils, like if it's really sandy, even if you did follow it last year, there might not be that moisture there anyway if it's been like a hot, dry finish and then a really dry summer. But I think if you have had some of that early rain, or, you know, particularly for the guys further north than you, but like if you have had the tail of a cyclone go through in late January or early February, you know that moisture's there, right? It's still going to be there at depth. And particularly if you've got those deeper monitors and you know the moisture's at depth. But the really important part is getting established. I mean, wheat is tough as nails once it's established, but those early couple of weeks, that's where you can really lose it. So you really need to make sure you've got that moisture for those first couple of weeks in the soil, to be confident that you'll get that establishment. You know, the root grows really fast. As you can see from Huyen's talk, like the roots get down so fast that they will get down if they can. Yeah.
Thank you.
Thank you very much for everyone who dropped the questions. I would like to have more discussion on, but we're running a little bit out of time. I'm pretty sure that you will be able to touch base with Sarah and Huyen, talk a little bit further in future occasions. I would like us to finish this day thanking you both for giving us your time, of sharing a little bit of your knowledge, because I'm pretty sure there is more that we can talk about these interesting topics. I would like to acknowledge as well the support of the Grow Group Alliance, who leads the Drought project, which allow us to be discussing this at the moment. And make everyone aware that the Resilient in Action webinars will be online, and you can get it in our YouTube channel. And I actually share a link in the chat if you would like to review some of the work that Sarah has done, some of what the Draw Hub is, some of the Huyen's research as well, and a little bit of what other options and available resources we have about drought resilience. Please, I would like to invite everyone just to come with us to the next round of the series. So we're going to talk about salinity and how to tackle it down from a practical approach. That will be in the next month. So I will be really excited to have you again in this space. Thank you very much, everyone, and have a beautiful day.
Yeah. Thank you.
Thanks, take care.
Yeah.